Now I'd like to move on to talk about the diatom, our algae strain that clients selected for us. Photodactyl tricornidum is a diatom, and it's one of two algae strains to have its genome entirely sequenced. What this means for us is that it's going to be good to know the entire genome for people like Dr. Noble who use that to be able to go in there, manipulate some enzymes, and get the desired properties you're going to achieve. Like I said, it's a tetanus diatom, and so one problem with this, you got asexual and sexual reproduction, like we were saying earlier, the company in Brussels. And basically, with the asexual reproduction, it'll go down to about a third of the size, and if you don't trigger the sexual reproduction properly, you're going to lose your algae culture medium. So that's one design issue that we haven't quite figured that one out. Like I said, it's important to drill down and really understand all these issues to make sure you have the best design. So, our algae is an autotrophic algae, as you all know. These light nutrients, CO2 in the water, and those all have various constituencies. So, what we did is we modeled a typical growth cycle for Photodactyl tricornidum. As you can see, we're batching out different amounts of algae. And what this is showing you that basically you get exponential growth as long as you aren't limited by your FAR, your photosynthetically available radiation, or your CO2 availability. So you'll get this exponential growth. And if you can maintain that exponential growth, if you batch out, the next one will show it a little more clearly. If you batch out smaller intervals more frequently, you're going to be able to maintain a higher rate of production. Also, the important things to consider are things like shear rates, basically the mechanical forces that act upon your algae cell to break them. Things like this can happen when you have your gas CO2 mixture coming in from your bubble zone. Well, I'm about to present another technique that I think will get you a better shear rate. But you want to try and optimize this so you aren't killing your algae cells with your gas mixture coming in. Also, when these little bubbles cavitate, they create microeddies, and a specific size microeddy. These are we designed for parameters found through research. So this will require testing to validate. Also, with your algae strain, you got to starve that algae to pump up that lipid content. Well, what happens is when you starve the nutrients, it basically consumes carbohydrates and pumps up its lipid content. If you can, this is just a model. This isn't actually Photodactyl tricornidum. It's another algae strain found. But if you actually can determine the amount of time that's optimal for your nutrient starvation, you'll get a higher lipid content algae. So the sort of thinking that comes with design, you start out with something really basic. So, well, we're going to need, we weren't going to do an open pond. That was never part of the deal to make it continuous and all that. So we start out with growth tank, separation chamber, harvest tank, water conditioning, central control, all topics which you guys know about. And this is our very first system diagram, what we thought we needed to do. So moving on from this, we came up with several designs. Tank system, coil system, tray system, modular system, and basically we model each of these using a software that we'll call Fluent. And what this allows you to do is really interesting things like mass transfer, heat transfer, fluid flow, and this chart right here is actually a velocity vector. You can see that you have your air coming in through the middle, coming around the outside, and that creates your agitation and your aeration. So agitation means the flow of fluid in your container. Aeration means the availability of CO2 to your algae strain. We also modeled a moving paddle using a different type of analysis of fluid. As you can see, there's a higher velocity vector around this moving paddle right there, so it's not as good as designed for that airlift technique. And this is also just a brief synopsis of some of the alternatives. If you want to get more technical and get actual numbers, I'm just presenting ideas so you can ask me after the presentation. We also use Fluent, you can model things like the density of your model your pressure. This is important for us because we plan on mounting our sensing on the bottom plate, and we have to ensure that, you know, you're not going to get leaks through your seals, and that basically your sensor is going to stand up. Also, what you get, this is what we kind of optimized with the 2D model. We're going to work on a 3D model that will incorporate photosynthetics, basically your PAR, your algae particles, and your fluid flow. So this is our preliminary findings we basically use this to optimize our dimensions for our tank. Then when we had these dimensions, we took this and put it in a hypermesh and used a program called Abscess to basically understand the loading and shear forces on our tank to make sure it stand up to, you know, accidental people falling on it, whatever. So you can kind of start to see we started out with a CAD diagram. These are the individual constituents. You can see you have your top and bottom plate, light columns where the LEDs are going to go, your draft tube, which is the inner tube where the stream comes up, and then it comes down to the outer tube. This is another one with modeling 6 light columns. And then what you got to consider is the number of light columns you want to get your light penetration depth optimized. And 4 columns was found to be cost prohibitive compared to, or 6 was found to be cost prohibitive compared to 4. So you can kind of see it from the top view here of the lighting system. This one we modeled 5 and this one 3. And this is a 7.5 centimeter spacing between light and wall. And that way you can optimize your LEDs to output the right power. So you get your correct light density as well. Here's a little chart I found showing light limitations. Basically, when those photons are emitted, you can have a point at which there's too much light and you get saturation. And that's based on your algae strain. It's going to only be able to absorb so much light. So here's another model of the LED light bulbs, this time in the container. You can see it. And then we move on to the actual lighting itself. What you got to consider here is we're placing a light in each of these tubes, so they're basically they're insulated from the water. But you could just epoxy these LEDs on these PCBs later if you would like. You got to make sure that you have enough field of view. And so basically, this isn't a very good diagram at all. It's no hash together, but you'll have red and blue LEDs, which are the spectrum components that algae best absorbs based on its chlorophyll content. And you can get each of these columns to get maximum light distribution in these chambers. Now we move on to the bubble size and gases. So I started to talk about this. Basically, your smaller pore size makes smaller bubbles. You have a higher surface volume ratio. They're better absorbed by the algae when they're smaller, although this can cause ruptures in the algae due to microeddies if you don't have the size right. And after a while, when you're growing a lot of algae, biofilm will deposit and you'll have to take your bubble stone out and clean it. So instead of using a typical bubble stone, we decided to go, there are lots of gas barging techniques you can use. Moss bargers have custom manufacturing process that ensures the bubble size. So this is a typical pipeline barger with a hole drill in it. And as you can see, here's millions of bubbles emitted by your gas barger, by your moss barger. And that's a picture of it right there. So we ended up with our final design. We have these subsystems. Mounting frames, this is basically just a Home Depot style mounting that can be reconfigurable, modularizable, and scalable. And so if you need to put another tank on eventually or more sensors, you can modify it. We have our gas input system, nutrient chamber, saltwater inlet chamber. Since our algae strains are marine diatom, you have to make sure the salinity is correct. Moving on, we had our cultivation chamber, which I talked about extensively. Our starvation holding